On behalf of my co-authors Valentin Schwind, Philipp Göttlich, and Niels Henze. So this work is about our system called PredicTouch, which reduces the touchscreen latency using neural networks and inertial measurement units. So touchscreens combine input and output in a single interface, which makes interaction more intuitive. And like all other input devices, touchscreens also have a certain latency. However, in comparison to a mouse or a keyboard, the latency is more visually apparent on a touchscreen. So, for example, in this image, you can see that latency results in a gap between the stylus and the writing. So when drawing a line or dragging an object across the touchscreen, latency results in a clearly visible gap between the stylus and the registered position. So this gap is visualized as dashed lines in this picture. So latency is nearly unavoidable on today's mobile devices, and this is because the touch input has to be passed to several components and layers before the output can be visualized on the touchscreen. For instance, touch input needs to be registered by the touch controller, it needs to be passed to the operating system, and needs to be processed by the application before the response is rendered on display. And previous work investigated touch latency and its effect on the user. So Eng and colleagues found that latency on commercial devices typically range about 50 to 200 milliseconds. And they also found that even a small amount of latency, even below 10 milliseconds, is easy to perceive and clearly visible. Jota and colleagues confirmed these results and further found that latency decreases the user's performance. Ritt et al. Showed the same and also found that latency above 170 milliseconds is regarded as unacceptable, especially in tasks such as drawing or dragging objects around. So how do we reduce touchscreen latency? Previous work presented different approaches, including software-based approaches and hardware-based approaches to reduce latency. So the hardware-based approaches involve additional and novel hardware, which is faster at capturing and faster at visualizing the response. These prototypes were mainly built to investigate the effect of touch latency on the user. So amongst others, Lei and colleagues developed a multi-touch sensor with a sampling rate of 4 kilohertz and used a high-speed projector to visualize the response. Similarly, Eng and colleagues used a high-speed camera to track the fingers and a projector to visualize the response. Katan and colleagues used a motion capture system and optical markers, which you can see on the right image, to capture the finger movements and use a high-speed display to visualize the touch. So the advantages of these approaches is that latency can be reduced down to about 1 millisecond. However, the disadvantage here is that additional and also bulky hardware is required to reduce latency. And therefore, they are only suitable for stationary setups, but not for mobile devices where users need to carry around these bulky devices just to reduce latency. In contrast, software-based approaches do not require any additional hardware. In general, these approaches reduce the latency by estimating the feature position of the finger to overcome the latency gap. So Katan and colleagues used a linear extrapolation based on the previous movements of the finger to estimate its feature position. So the extrapolation reduces the gap between the registered position and the actual position. So this is shown as a red line in this image here. And Henze and colleagues improved this approach and trained neural networks to estimate the feature touch position. So while these approaches work without any additional hardware, they include prediction errors. So the prediction error is the gap between the estimated position and the actual position of the touch in the time of the estimation. So that means that wrong estimations that are rendered on a display are perceived as jitter and can even decrease the user's performance and accuracy. So while software-based approaches can be used on mobile devices, they also induce jitter, since the prediction is not always correct. And this is where our system comes into play. So we present a hybrid approach that uses neural networks similar to the approach by Henze and colleagues, and we combine it with inertial measurement units to reduce the prediction error. So these inertial measurement units, in short IMU, consists of an accelerometer, a gyroscope, and a magnetometer, which we use to capture the micro movements of the hand while it performs input on a touchscreen. And these micro-movements give the neural networks more information to predict the feature touch position. So we captured the micro-movements of the hand on different positions by placing the IMU on the wrist, on the finger, and also on the stylus. And we choose these positions because they can be replaced by wearable devices such as a smartwatch, a smart ring, or smart pens that include the IMU on the top of the pen. So therefore, our approach can be implemented on nowadays mobile devices without requiring the user to carry any additional hardware just for reducing the touch latency. So we first built a prototype of this approach and then conducted a data collection study to collect the ground truth data to train the neural network. So our system consists of 3 IMUs attached to the stylus, the finger, and on the wrist, as we can see on the right of this picture here. And these IMUs are in turn connected to the Arduino. The Arduino reads the sensor values and streams them to this Nexus 7 tablet, which connects the IMU using a USB OTG cable. The Nexus 7 logs all the input made on a touchscreen, the touch input, and also the IMU sensor values, while the user is drawing on the touchscreen. So we conducted a study to collect the ground truth data for the neural network, and we asked participants to draw, to write, and to perform a Fitzler dragging task, similar to the approach by Henze and colleagues. So in the drawing task, we instructed participants to draw images of their last vacation, where in the writing task, they had to copy a text which we gave them. And in the Fitzler dragging task, they had to drag a tile into a target shape, which we can see on the bottom right of this image here. And participants performed these tasks using the finger ones and also the stylus ones. For the study, we recruited 18 participants, whereas 50% of them are female. So the collected dataset consists of about 1 million touch samples from the touchscreen and about 28 million samples collected from the IMUs. For each touch sample that we collected from a touchscreen, we matched the corresponding IMU samples by using the timestamps as the matching criteria. So using the collected dataset, we trained neural networks to predict the feature finger position based on the previous hand movements and touch positions. We actually trained multiple neural networks with different IMU combinations to find the one model with the lowest prediction error. As input, we used the 10 latest directional vectors of the touch samples, which we also made position and rotation invariant. And for each IMU that we used in the model, we included the 10 latest samples of the IMU. And as output, we have the X and Y position of the feature touch positions in steps of 60 milliseconds. So we choose these steps since this corresponds to the sampling rate of a 60 Hz touchscreen. As the architecture for the neural networks, we use 3 hidden layers with 500, 400, and 300 neurons, and use the adaptive gradient algorithm, in short ADAGRAD, as the optimizer for this. We also use the Xavier initialization scheme to initialize the weights of the neural network and use the constant initialization for the biases of the neural network. So these box plots show the errors in pixels of the different models that we trained. So the gray box plots represent neural networks that use only the touch samples, which is also the approach by Henze and colleagues. And all other box plots represent the different combinations of the IMUs that we trained. So in general, what we can say here is that we found that using any IMU combinations reduces the prediction error significantly in comparison to using just the touch samples. And the best model for finger input is using the IMU, which is placed on the wrist. And for the stylus input, the best model is to using the model that has the IMU on the stylus itself. The average prediction errors in pixels are about 9, 21, and 35 on average for the 3 prediction levels 0, 33 milliseconds, 66 milliseconds, and 99 milliseconds. So here I will show you some video demos of our prototype and how it works. So this video shows the touch latency without any prediction. So this is what you get when you use the Nexus 7 out of the box. And as you can see, there is a clearly visible gap between the stylus and the writing of the word hello here. And this shows how it looks like when we use the approach by Henze and colleagues using just the touch samples. So as you can see, the gap between the stylus and the writing is smaller, but there's also clearly visible jitter involved when you write the word hello. And this is how it looks like when we use our approach with a 33 milliseconds prediction using the IMU placed on the stylus. So here you can see that the jitter has noticeably decreased in comparison to the previous video. And this is how it looks like when we use a prediction of 66 milliseconds into the future. And what you can see here is, while the gap is smaller, there's also much more prediction error, means jitter, involved. So after we developed the model and found the best IMU combination, the next step is to evaluate the effect of the latency reduction on the user. So we conducted a user study in which participants used our system, once with a stylus and once with a finger input. We let them use 3 prediction levels, means 0 to 66 milliseconds, whereas the prediction were once with and once without the IMU. And this results in 10 conditions in total, since a prediction level of 0 milliseconds cannot make use of an IMU. So each condition consists of 2 tasks, a Fitz-Law task and a pointing task. In a Fitz-Law task, participants had to drag a tile into a target shape, which you can see on the picture on the right. In the painting task, we instructed participants to draw a picture of an island. So we used the Fitz-Law task to determine the throughput, which is a combined measure of accuracy and speed, and we used the painting task to collect qualitative feedback on the latency reduction. We randomized the order of the conditions and recruited 16 participants for the study, also with a 50% rate of female participants. So we found that using the IMU significantly increases the average throughput. So the throughput with IMU are shown in red, and without are shown in blue. And we also found that the prediction levels have a significant effect on the average throughput. So this means the higher the prediction level, the higher the throughput. When participants rated the lag and unpleasantness on a 7-point Likert scale, we also found that significant less lag was perceived when an IMU was involved. Further, participants perceived more unpleasantness for higher prediction levels because there's much more jitter involved. In general, participants mentioned that lower latencies are less frustrating and have a better accuracy. So based on their own experiences using touchscreens and also the experiences in the study, they envision that latency reduction can be especially useful for use cases such as drawing, gaming, and also writing applications. So our contribution is a system called PredicTouch, a system that uses the neural networks and inertial measurement units to reduce the touchscreen latency. And in comparison to the previous approaches by Henze and colleagues who used only the touch samples, we could show that including IMUs decreased the prediction error significantly. And as a result of this latency reduction, we showed that the user throughput can be increased by up to 17%, where they perceive noticeably less lag. So in future work, we plan to investigate more specialized models like recurrent neural networks or long short-term memory models to further reduce the prediction error in general. And also we want to investigate techniques known for machine learning competitions such as ensembles, bagging, or boosting to reduce the prediction error. So thank you for your attention, and I'm open to any questions now.
Hello, Benjamin, also from the University of Stuttgart. Do you also use the IMUs from the smartphone or tablet to train your data?
No, we only use the IMUs that we place on the hand to capture the micro movements of the hand, how it moves on the touchscreen. We did not consider the IMUs in the tablet itself. And also the reason why we did not do that is that the accuracy and the sampling rate of the IMU in the tablet was not as accurate as the one we could get from the external sensors.
Okay, so I was just thinking because if you look at Daydream, where they have special requirements for the IMUs itself, maybe they're appropriate to get rid of external sensors and maybe apply the same mechanism to the internal measuring units with your prediction capabilities. So I think it would be interesting, but it's nice work.
Yep.
Other questions? So yeah, I wanted to ask about RNNs and LSTMs. I was wondering why you didn't start with those networks which are designed for time-based data, which have the feedback loop. So you used a feed-forward network, is that correct?
Yeah.
So why did you choose that network and not RNN right from the start?
So the reason is there's previous work from Henze and colleagues who used a neural network just on the touch samples. And what we wanted to show is the effect of adding the inertial measurement units to improve the prediction error in general. So the RNNs or LSTMs will be basically the next step to reduce the prediction error in general, which could also be applied on the touch sample approach by Henze and colleagues.
Did you do that? Are you going to do it next, or have you actually tried it already? With
So for only the touch samples, there's actually a poster at this year's Mobile SIGCHI, where we showed that just applying the LSTMs already reduces prediction error, and this can also be applied on our approach with the IMUs.
Questions? So maybe a last quick question. So for the stylus, you use that the smartwatch, but you could also integrate the IMU inside the stylus, as has been shown in some projects. Do you think that would increase the accuracy to have the IMU closer to the tip rather than just on the wrist?
So actually, for the IMU use case, we used the IMU on the stylus itself.
Oh yeah, okay.
Yeah.
So with
So for writing, it was on the wrist, and for using the stylus, it was on the
right.
tip.
Okay, so let's thank our speaker again. And